Hi everyone, welcome to Ventilator Engineering. Today we're going to be talking about how to spec flow control components for your critical care ventilator. This video is intended for people who may have found a design that they like online and are trying to figure out how to locally source parts, or for people who are designing a ventilator from scratch and are trying to understand the full scope of specifications when performing their engineering design. So for today, we're only focusing on flow control components. That means things like mass flow controllers, pressure regulators, proportional and solenoid valves, things along those lines. We're not looking at things like sensors and fittings, but I hope we can cover those in future videos. So look out for those. To begin, I just wanted to go over this simplified block diagram that we mentioned in the last video. I think a lot of designs that are out there fall within this general scheme. If your device does not, don't worry, we'll still provide some tips that I think will be useful to you as well. But for now, we're operating under the assumption that the hospital will be able to supply wall O2 and medical air and has an existing gas blender for mixing those. But equivalently, you can make the assumption that you can use an O2 canister and compressed air and maybe a simplified dual venturi system for handling the mixing. All of that's still kosher. Downstream from there, we have our first flow controller block. That's one of the portions of the device we'll be considering today, followed by a number of sensors, maybe your O2 and pressure sensors, and some flow safety components, potentially a pressure release valve or an emergency breathing valve, devices like that. Then we move into the device externals. Here you'll find the humidification system. This may be either a heated humidifier or an HME, a heat and moisture exchanger, as well as the rest of the respiratory circuit that leads to the endotracheal tube of the patient. Moving back into the device internals, we'll have additional sensors. Here you'll find your expiratory flow sensor, as well as additional flow controller components. And this may include your PEEP valve and your high frequency solenoid, whatever you have going on in here. So this is the rough scheme. And the question is, how do we go from this sort of conceptual block diagram to a bill of materials that we can go out and order and assemble into a working device? So for now, we're just focusing on the flow control components, and we want to understand why these present such a design challenge. So I think it's good practice when doing design work to sit down and understand the entire flow circuit and try to characterize which parts of that flow will impact your design. So that's sort of what we're going to be running through here. The first consideration along these lines is the pressure drop. So if we're operating under the assumption that we're getting our gas supply from a hospital wall, we can assume that the wall O2 and medical air will be supplied in a pretty regular way at around 50 psi. But by the time the air gets to the patient, we're operating within a pressure regime less than 1 psi, specifically less than around 0.6 psi. Ventilator specs are often given in CmH2O, so often we'll be operating under 40 centimeters H2O, right? So here's a substantial pressure drop just across this first flow controller block. Additionally, we need to be mindful of the airflow. So in addition to a low pressure, which is supplied to the patient, we also have a pretty high airflow. This is within the range of 60 to 120 standard liters per minute. So already with these two design considerations, we've become very limited in which devices we can place within this flow controller block. So if I wanted to source a mass flow controller that works with this high flow, low pressure regime that we've set, it may cost me on the order of $2,000. If I want a spec or proportional valve that works within this regime, if I'm operating on the high pressure assumption, around 50 psi, that type of prop valve will cost me around $100, compared to a prop valve that's spec'd for the low pressure regime, which will cost me maybe $700 or $800, depending on where I source it from. So being mindful of these specs may save you a lot of money in addition to making your device safer and more functional. So it's all really worth considering. We have a few other considerations. I won't be able to list everything within the span of this quick video, but the humidification system boosts up your heat and humidity. I think this is more applicable to those who are sourcing sensors, but it's worth noting that you're going to be operating at 100% relative humidity at 37 degrees Celsius, provided by your humidification system. And there are a bunch of other considerations as well. You really need to think about material selection, especially because this is a biomedical device. You may think if you want to avoid substances such as brass, which may be leaded to ease the casting process, and may also interact badly with high oxygen levels, especially if the doctors boost up the oxygen concentration to closer to 100%, which only happens in rare cases, but it's still worth thinking about. You need to spec for which fittings you want to use within your device. So I try to select for valves which give us 1/4-inch NPT fittings as a standard fitting. You need to understand how your valves are actuated. Some of these solenoids may require pressure drop assist. So if you're operating within this really low pressure regime, your valves may not even open in the way that you expect them to if they were a zero pressure drop assist. And additionally, we need to be very mindful of the CV. This is the flow coefficient, because we don't want to restrict the flow unintentionally, especially if this reduces the airflow to the patient. So all of these are worth being mindful of. Cool. So in terms of spec'ing flow control components, the first thing we want to do is think about where we might be sourcing from. So I think that a lot of engineers sort of start off with a list of known companies that they've sourced from in the past. If you're not familiar with good companies in your geographic location, you can reach out to engineers that you know who have been working in this field a little longer. But usually there's a set list that you turn to first. So here I'm operating in the northeastern US. So if I'm looking for hardware, a pretty solid choice is McMaster-Carr. And I'm not trying to plug any companies, but they're generally reliable in terms of having reasonable tech specs and shipping very quickly. So if you need to do rapid design, that's a pretty good choice. If I'm ordering electronics, I usually get stuff from Mauser, especially in this COVID crisis. They've been extremely fast in terms of turnaround, often expediting the shipping to one-day shipping without anyone having to pay for it on our end, and to a lesser extent, companies like Newark and DigiKey. If I just need some basic supplies like standard NPT fittings and pneumatic tubing, I can just go to a local hardware store like Home Depot. And if I want some fancier flow control components, I have a few companies that I like to look for first. These smaller specialty companies include places like Omega, but they do tend to be more expensive than some of the other hardware suppliers. And just one more thing to be aware of, if you do need to buy some specialty medical equipment like HEPA filters and heat and moisture exchangers, you may need to work directly with the doctor to get a prescription before you can order these parts online. So all of that is worth being mindful of. So rather than give you a list of specifications that you need to be mindful of, I wanted to do a quick sourcing walkthrough on the websites of two of these companies that I've mentioned. And those are Omega and McMaster-Carr. We're going to source from two different parts of our block diagram. In the first case, we're going to be looking for a pressure regulator, and we'll look at Omega for some of these components to see what it looks like when we actually go out and source stuff. And then secondly, we'll look for an expiratory control solenoid, and for that, we'll be operating, of course, on the expiratory end of our circuit, and there we'll look at McMaster-Carr. So just to begin with the pressure regulator, let's do a walkthrough on their website. So I'm going to go to omega.com, and we're going to try looking for a pressure regulator. And I hope that even though this is a boring part sourcing walkthrough, that someone can benefit and be mindful of some type of spec that they may have missed. So I'm just going to narrow my search down to actual pressure regulators. And since we are working within a pretty specific pressure regime, I'm going to try to narrow that down as well. So I'm going to pick one of these lower end restrictions, and I've dropped my search down to just a few categories of parts here, right? So just skimming through what we've got here, we have these miniature pressure regulators. And immediately when I see these, I become worried that the CV won't be high enough. That's the flow coefficient. So I worry that these tiny little inlets will be restricting my airflow and it won't work for our application. We have some other pressure regulators. We have a high flow application pressure regulator. So that's pretty promising. And then more specialized things like regulators for harsh environments, which we don't necessarily have here. But all of these are worth considering. I'll look into that a little more closely later, although it is quite expensive. But just to quickly run through some of these, I'm going to compare the miniature pressure regulators to the high flow pressure regulators. Okay. So let's start with the miniature one. I assume that this one will not work, and we'll see if that's true. So I'm going to drop the pressure range down to the smallest one available, 0 to 5 psi. And happily, these are in stock if they work. I see that the port size is pretty small. I was hoping for more like an 8mm pneumatic tubing type size, but we may be able to work with that if it actually suits our purpose. And then I'm going to scroll down to the product details. And immediately, the first thing I'm going to look for is the flow capacity, because my suspicion is that it will not be able to flow enough for our application. And indeed, it looks like it probably might not. If you remember, our airflow specifications were that we were shooting for 60 to 120 standard liters per minute in terms of flow. But here, it looks like we're limited to around 71 liters per minute. So this may indeed be too small for us. We could look into the data sheet to see if there's any additional information, but for now, I'm gonna nix this one. Let's compare the air pressure regulator that was specifically designed for high flow applications as well. So again, I'm gonna set the pressure range down to the one that fits our specs a little better. And indeed, this one is in stock, so that's good. And immediately I noticed that it fits my fitting qualifications. It's 1/4 inch NPT, so that's something that I'll be grateful for if this part works out. And then I'm going to drop down again to the specifications. So we can skim these and see if it works for our purposes. I'm not totally worried about the exhaust capacity just from this, because we're not really operating within this pressure range. Sensitivity is pretty reasonable. Our upper limit is 40 cm H2O. The sensitivity here is eighth of an inch H2O. So this is tolerable. And then I'm gonna, after skimming these, open up the data sheet, because in addition to the actual technical drawings of the device and the complete list of specifications, what I'm really looking for is this performance curve diagram. And I'm sure there are much better explanations of how to read these online, but it's really important that you check the performance curves of a pressure regulator in similar devices. Okay, so the way we read these performance curves is that we look at the inlet pressure that they've specified here. This is assuming that you have 100 psi at the inlet of the device. And then the rest of the plot is a flow versus outlet pressure plot. So here's our little 0 to 2 psi regulator performance curve down here with 100 psi supplied to it. And according to how much flow is supplied to the device in cubic feet per minute, we look at how the pressure drops off as a result of that. Okay, so this is in cubic feet per minute. So in terms of the flow that we have, 60 to 120 standard liters per minute, we're down here in this lower portion of the performance curve. And what I'm looking for here is nothing super quantitative or precise, because this is a performance curve for a higher inlet pressure than we have, but I'm really looking for the linearity of this curve. I can assume that the characteristic of the curve will be conferred over to a 50 psi supply pretty reasonably. And because this is pretty linear, I'm confident that this regulator will probably still work for our application. So it's really important to look for these performance curve plots and see if you can understand to what extent this device will work for your application. Okay, hope that wasn't too confusing, but it's really important to check for these. Okay, so I'm pretty happy that this regulator would work on that inspiratory block from our diagram. That's this guy. Okay, so having found a reasonable candidate for that, I'm going to start looking into the expiratory control solenoid. And for this part, I'm going to go to McMaster-Carr and see what we can find there. I'm going to go to mcmaster.com and search for solenoid valves. Okay, great. So in searching for that on McMaster, I see a number of different options that we may consider. There are on-off valves. That's what McMaster-Carr calls process valves. We see some maintenance parts, diverting valves. I don't really care about. Maybe you will use these in your devices. Flow adjustment valves, hydraulic valves. I also don't care about hydraulics, and I don't care about drinking fountain replacement parts. We're really focusing on these two categories of devices. So we're comparing these process valves to these control valves, and both are types of solenoids. I'm going to start by looking at the process valves here. Okay. So process valves are distinct from control valves in a number of ways. They're usually visually distinguished by these little caps that cover the solenoid. They usually lack exhaust ports, which may be useful for your device. And they usually have larger flow coefficient, larger CV, and are slower than control solenoid valves, right? So these process valves are typically used for moving around process fluids. If you're in the food and beverage industry, this may be moving around milk, right? So if we scroll down to the bottom here, we see a bunch of different process valves for moving things like chemicals, for moving things like cryogenic liquids, drinking water, gas, and so on. And if I look at one of these, one of the things I want to be mindful of is whether or not they are pressure drop assisted. So if I were going to put this type of valve on my expiratory side, we know that we're operating at a very small pressure drop, right? So we may not get enough pressure to even actuate this valve at all. It may not open if we have it on the expiratory end. So I want to be very careful about choosing a device that requires zero pressure drop. Okay. But for my application, I'm looking for a high frequency solenoid. So I'm not going to use one of these on-off valves. I'm going to go to this second category of solenoid valves, the compressed air solenoid valves. Okay, so there are a number of options within this category as well. There are entire manifolds of devices. There are hazardous location control valves. But immediately I noticed the difference between single action control valves and two action. So the difference between these is that the single action valve typically has a spring within it. So it's either normally open or normally closed. You actuate it to put it into the other state, and then a spring will switch it back to the original condition. The two action control valves actually have two independent control modules to flip back and forth between the two states. So I know from experience that looking through these valves, the McMaster two action control valves don't actually tend to be that much faster than the single action valves. So I'm going to look at this fast switching single action control valve section first if I'm doing part spec'ing. Okay, so now looking at this website, let's see what we have. We have categories based on whether the valves are normally open versus normally closed. So depending on your application, this could really impact the safety of your device in the event of mechanical failure. So if I have a valve that's very close to the mouth of my patient, I may want it to fail open in the event of some mechanical failure so that the patient can attempt to breathe normally if they're still physically able to breathe. So be very mindful of this when you're designing the safety components of your device. You may want it to fail open. So I'm gonna design for that. I'm gonna have mine normally fail open. And I'm going to look at these inlet and outlet tube diameters. I prefer these 8mm ones because that fits my standard pneumatic tubing size. And then I'm going to look at the rest of these parameters here. So they give flow rate, specification, they give a flow coefficient, which is pretty small. We have to think about whether this is large enough to flow for our specific application. That's one benefit of getting away with process valves if you can. But we're going to think about whether this is too restrictive for our application. I check the pressure range to ensure that I'm not limited here, that the valve will still actuate to some degree and I'm not exceeding any of these bounds in any way. Vacuum rating. So I found that the 12-volt DC solenoids tend to have a larger flow coefficient than those that take smaller voltage levels. And then I'm going to look at the product detail to see if there's anything I'm missing here, such as this speed. Let's see how quickly this actuates. I think I have to go all the way down to the bottom to check that it shifts between flow positions in 1.7 milliseconds. So if you're doing some type of PWM-based control, you need to understand if this is going to be fast enough to handle your control scheme. Okay, so I may consider this as a potentially viable solenoid option, but I'm probably going to spend a little bit more time online to see if I can look for anything that has a bigger flow coefficient. Okay, so I hope that these quick walkthroughs provided some details that can help you look for parts for your own device. And please feel free to ask any questions. We can do more sourcing videos for parts that you actually care about if they weren't covered here today. So thanks for watching. Bye.